Welcome to the second lecture about descriptive statistics. I'm going to continue with from where we left. In the previous lecture, we basically talked about descriptive statistics, but especially graphical methods. And the common motive in these graphical descriptive statistics is to show a general distribution of the data. And stem and leaf diagrams, we seen that stem and leaf diagrams were more detailed representations. On the other hand, histograms are more coarse-grained representations, lower resolution representations, but they give a very good summary of the whole data. Now, today we are going to continue with numerical methods in describing our samples. Now, why do we need numerical methods? Because is the title suggests, graphical methods gives you only a visual understanding, and visual understanding may change from person to person. It's a little bit subjective. On the other hand, if you can come up with some numbers, then they are much more objective. And let's start with those numbers. What type of numbers we can use to describe our data? All right, so the most common method that we have already known and is pretty much used is sample mean, right? Which we learned from high school. But what does sample mean actually suggest, or what does sample mean denote, represent? So here there is a higher heading here. It says measures of location. Now the important word. So I'm going to maybe a little bit went a little bit of a frustrating way, but actually numerical methods are divided into a couple of different categories. And the first category comprises the measures of location, and sample mean is an example of that. But what is a location of data? Actually, it shows the central tendency of the data. Now, this is still not a very clear, but a little bit of an elusive concept. The idea comes from, if you remember from the first lecture, I likened the data, likened the data to an organism. Well, if you are talking about a human, for instance, then the two-dimensional projection of a human on the ground is actually a small area, so the location is a pretty much small area. But think about a snake or a dragon. Then if you are going to ask the exact location of a dragon on ground, then it is difficult to describe that because spans a large region. But we need a single value to measure its location. So, well, you can take, for instance, the part of the dragon which has the highest mass, right? That may be one measure of location. Or the part of the dragon which has usually a uniform and also a large mass for a region. You can call it a location of the whole of the dragon. So let's come back to statistics. When it comes to data, since it's distributed over a region with different accumulated, let me say, densities, then it's difficult to directly pinpoint the location of data. So one metric that we use is sample mean. It is directly, as we all know, we just take each of the observation in the sample of n observations, we sum them and divide it by n. This is the summation sign. Please get used to this representation from I1 to n, and we divide it by n, which is the total number of observations in the sample, or it is also called sample size. So basically, it's, for instance, on a dot diagram, if these are our observations of the sample will be somewhere here probably, if you just take the mean of the location of these each observations. So the location of the sample will be somewhere here. Actually, the location deemed by the mean or suggested by the mean will be here. So, well, as you should realize, this single value here, think about, like, if you go back to our first example, it was like 16, 17, 18. This would be something like 17.50, let's say. Well, as you should realize, as opposed to a dot diagram, a single value represents or gives only a small amount of information about the whole data. So it may not be sufficient to describe the whole data. So that's a disadvantage. That's usually going to be a disadvantage of all numerical methods, right? As opposed to graphical methods. On the other hand, there is a large advantage. A single number will denote or will represent the whole data. So if we can come up with a couple of those single measures, but all measuring different aspects of the data, this may be an alternative to graphical procedure, because it's going to be a list of different values, and from this list of different values, of course, it should be a small list. Otherwise, if it's as long as all the observations in the sample, that would be meaningless, right? We can get information about the whole sample. Now, one thing about sample mean, does it represent the population well? Well, for this case, this seems to be okay. It gives a good indicator of where the sample, where the location of where the data generally resides. But on the other hand, think about a sample like this, right? A histogram is plotted here. As you can see, there seems to be two peaks. I'm going to talk about in a couple of minutes. I'm going to call this bimodal distribution. So the lowest populated region, if you probably take the mean of all these values, since these are like, well, this is very much like the center of mass in physics that you have learned. So if you think each of these as mass, and if you take the center of mass here, it's going to be somewhere here. Well, in physics, that's okay, the center of mass being here. You can assume that whole mass is accumulated here, then you can all do the calculations about torque or whatever. That's nice. But in statistics, then when you find the sample mean here to be at this point, and you assume that sample mean is the most typical value of observations, you are totally wrong about that. In especially bimodal or maybe trimodal or more than one mode of observations, I'm going to explain what mode is in a minute, then the sample mean of observations is not a typical value. Does it show a central tendency? Well, actually, I don't think so. It shows still a central tendency. There seems to be two central tendencies here and here. So you should be careful about, if you just report a single sample mean value, it may be deceiving if you do not supplement the sample mean information by other graphical or numerical methods. But for many cases, if you have a single peak here, right, sample mean seems to be a good indicator of central tendency. I'm going to talk about this more at the end of this lecture. Okay. The second numerical statistics that we can use to describe the location is, probably you are also familiar with this concept, is median, sample median. The idea is very simple. Instead of just adding the values one by one and divide by n, we rank order all the observations. What do I mean by rank order? We write the smallest, then the one just above the smallest to the largest observation in the sample. Then we find the value which is just for the 50% of the values will be on the left hand side, and 50% of all observations will be on the right hand side. Now note that depending on the sample size here, well, this should actually be capital N here. I start with capital N, then it turns out to lowercase n. I'm sorry for that. So if the sample size is odd, then simply sample median is going to be equal to n plus 1 over 2, the element at this point. I'm going to explain why this is so. If n is even, however, there's not going to be, the median is not going to be one of the observations in our sample. It's going to be found by interpolating two successive observations. So let me try to give an example here. For instance, if these are our observations, then we are going to rank order them. Well, rank ordering is usually written in this fashion. You use a subscript and you use a parenthesis here, like that. So when you do that, since we have 7 observations here, we are going to have 7 rank ordered observations. The smallest value here is going to be 0. then the next value is going to be 2, then the next value is 3 and 4 and 6 and 10 and 12. Well, without using any formulation, you can easily see that 4 is the median because it divides the data into 2 halves, right? So it's just 50%. If we use this formulation, since n here is 7 is odd, therefore, note that median is shown with a tilde. I'm sorry, I think I skipped that. I forgot to show it. Sample mean is shown by an X bar. That's an important thing. And sample median is shown by X tilde. X tilde is going to be equal to X. Here we have 7 observations, 7 plus 1 over 2, which is going to be X 4, which is actually equal to 4 here. Note that this 4 here, the 4th ranked observation, has got nothing to do with 4. So basically, if you are not given this set, but you ask, just tell me the location of the data, the median of the data is equal to 4, gives you an idea about the location of the data. So if we use the other location value, which is actually X bar, which is sample mean, if you add all the values, right, and then divide them, so it's going to be from I is equal to 1 to 7, xi over 7. This is going to be equal to 37 over 7. I guess it is almost equal to 5.3. So here, these are 2 different location estimates. Sample mean says that location of the data is at 5.3, the median is 4. Using these 3 location estimates or location statistics, actually you don't always, you are not required to use only one of them. You can use both of them. In most cases, we report all of these location statistics to give you a better idea. So both of them are pretty much close together. Although we got no information how much this data is scattered, right? So what's the maximum value, what's the minimum value? I'll come to that. Generally, the central tendency of the data seems to be around 4 and 5, which seems to be very consistent. Okay, let's do the same thing here for this data. So I'm going to do this, x1, x2, x3, x4. So we got 1 here, 4 here, 5 here, and 95 here. Note that this time n is equal to 4, an even number. And in this case, when you have even number, actually there is not going to be a median from the list directly. Why? Because there is not, there should be a virtual observation here between those two, from 2 entries, so that it's going to divide the whole set into 2. And that's exactly what this equation says. In this case, x tilde is going to be equal to xn over 2, which is 4 over 2, plus x 4 over 2 plus 1 over 2. Basically, it is the second observation and the third observation divided by 2. So actually, it's going to be equal to 4.5. So the location of this data suggested by sample mean is 4.5. That's great. What about sample mean, you may say? Now, when you find the sample mean is going to be equal to 1 plus 4 plus 5 plus 95 divided by 4. And the result is, where is that result? I think it's 26.3. Now, when you report these two, there seems to be high discrepancy. Now, if you're a little bit experienced, and actually at the end of these lectures you are going to be, you should realize that these cases usually correspond to there is one or a couple of outliers in our system. What do I mean by that? Now, there is an important concept, which is actually a pretty much important statistical research field in something like 50 to 40 years, and still it's an important area in statistics. These are robust statistics. Well, let me first give examples. Sample mean, for instance, is not a robust statistic. On the other hand, sample median is a robust statistic. What do I mean by that? A robust statistic is a statistic which is not easily affected by outliers. Why is, for instance, sample mean easily affected by outliers? Although actually 3 of our observations, think about as grades. We have only 4 students, and these are the grades they have obtained in a midterm. Well, if you, for instance, announce the average grade 26.3, the whole class, the first 4 students, if they do not know their individual grades, they think that, oh, that's not so bad, right? However, when you report the median, it's a different story. So a better, more reliable, more, I may say, correct description of this data is reporting the median. The median is 4.5. However, there is also an outlier of 95. Without reporting all these 4 values, just these 2 values, the sample mean is 4.5, and there is an outlier at 90.5, gives a more complete and much more realistic, reliable description of the data, instead of just using sample mean as 26. As I said, the sample mean is easily affected by outliers, and 26.3 is not a typical value. There is no the observation which corresponds to that value. On the other hand, note that sample median is not affected by outliers. Why? If this 95, of course we are talking about grades, it cannot be higher, but if this would be 9,500, sample mean, note that wouldn't have changed. If this were minus 1,000, still sample mean would have been equal to 4.5. On the other hand, changing these values, the highest and the lowest values, are going to affect easily and are going to have drastic effects on sample mean. That's why median is a robust measure, sample mean is not a robust measure. In statistics today, usually we report both the robust and non-robust measures together to give a more complete understanding. Well, one may say sample mean seems to be a better method here right now. So why did we learn sample mean, and why still I suggest using sample mean? There is something called efficiency also in statistics. Sample mean under some circumstances, later we are going to talk about, actually sample mean becomes the most efficient statistic. So it's also very important. So usually both of them are used together. Okay, the next measure of location is the mode, which is slightly less frequently used compared to mean and median, but still, as we are going to see, it's very useful. The idea is very simple. We just count the number of occurrences of each observations, and we take the observation with the largest number of occurrences. An example, I think, will solve it. So x is equal to these values. Let's say these are the grades of a class between 0 and 10 from a midterm exam, and we would like to describe the location of this class. So what we do is we take each observation one by one. For instance, 1 here, there is one unique observation. It only occurs 1 times. Now, when it comes to 3 here and here and here and here, it occurs actually 4 times. And if you continue counting these, for instance, the next observation is 4, I guess, it occurs only a single time here, and we have 6 here, it occurs 2 times. The largest number of occurrences is by x is equal to 3 observation. So it occurs 4 times. Therefore, the mode of the sample is going to be equal to 3. So when somebody asks you, okay, that was, let me say that I checked all your exam grades, but I won't going to announce all of them one by one, but the mode of your exam results is equal to 3. When I say that, you should realize that the most commonly obtained grade is equal to 3. You should realize that this is slightly different. This gives a slightly different information compared to mean and median. Actually, both mean and median seems to be, actually mean strictly uses all the given information, and median also uses all the rank information of all observations. On the other hand, mode only concentrates on the most frequently obtained value. So it's a little bit of a, I guess, a weaker central tendency measurement or metric, but it's still very useful. I think the use is going to be more apparent here in the second example. let's again say let's continue with the same scenario. Again, we have an exam of this many students. So we would like to describe the location of this data, and we are going to use mode. So what we do is, again, count the number of observations. I'm not going to do each of the unique values. It's going to take a long time, but you should see that 3 occurs here, 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 and here, actually 4 times, and 6 occurs here, 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 and here 4 times. So both 3 and 6 occur 4 times equally. None of the other observations occurs as much as many of these observations. Therefore, for this system, mode is you do not select one of these values, you report both of them. And this is a very nice additional information that cannot be captured by neither mean nor median, because this is what we call bimodal system or bimodal data distribution, I may say. So for bimodal distributions, or maybe a multimodal distributions, mode is a very nice indicator, because I can show you this example again from the beginning. This is a typical example of bimodal distribution in histogram representation. Well, actually, we don't know the exact values here, but there seems to be an accumulation of values here, and there seems to be accumulation of values here. So there seems to be 2 peaks here. So if these are symmetric, they don't need to be, but if they are symmetric, sample mean and also sample median will come out to be somewhere in the center. And if this is the case, note that this is the least populated region, least typical values are observed or are indicated by sample mean and sample median. On the other hand, the modes here will give us information more about the more typical values. So especially if you have a multimodal or multimodal distribution, it is very much informative to also find its mode. One last point here, if you have real values here, note that we have integer values. That's very nice when you have integer values. But if you take, for instance, temperature measurements of some, I don't know, some reactor, then the temperature measurements would be like, I don't know, 125.4, 360, 89.5, all these values. Now, note that if you have, let's say, we have 100 values, since we have here 4 significant figures, and there may be more, it is very highly unlikely that any of these values will be repeated. And even if it's going to be repeated, it's going to be probably due to chance alone. So it's not a very good idea if you have here real numbers, just to count the number of occurrences as we do for integers. What you should do is first convert this to an integer form. So how can you do this? You should discretize these values. And one way to do this is like the one that we have applied for constructing histograms. So what you would do is possibly, for instance, you may say that for values between 120 and 130, I'm going to use 125. So all values, for instance, this one will be converted to 125. If we have another observation here, something like this, this is going to be another 125. And this one will be whatever this range suggests. So when you actually make these, convert these, each of these real numbers to integers, then there would be some repeated integers, and then you can use the mode and come up with the result here. But you should always mention the resolution that you have used here. For instance, now we use a resolution of 10 degrees or 10 units here. So we coarse grain the real axis and turn it into integer values. Okay, that's enough with mode. And what about quartile? Quartile is also very much commonly used, and it's going to be also used by a method called box plot. I'm going to explain at the end of the lecture. The idea is very simple. We find the medians of the medians. So we divide the rank data into 4 equal intervals. So if we have 1 to n observations, you rank order them. The one in the middle is what we call median. And note that here is going to be also called second quartile, and it's going to be shown with Q2. So basically Q2 is median. Q here represents quartile. 2 means the second quartile. Because quartile, quarter, it comes from quarter, so dividing into 4. So we have two 1/4 elements, so it is 1/2, so therefore it's median. If you use this approach, the median of the first half is going to be this element here, and it's going to be the first quartile shown with Q1, and this is going to be by the same logic, it's going to be the third quartile here. There are other names given to that. For instance, this is also called 75th percentile and 25th percentile, but I think that's pretty much sufficient. So how do we compute quartiles? Well, actually, there are a couple of different methods to compute quartiles. Actually, if you just search for internet, you are going to see some of them. But I'm going to try to, using any of them will be sufficient for us because this is only descriptive statistics, right? But for, I'm going to use the method that is introduced in your textbook. What we do here is, actually, if you go back, we are going to be using these equations. For instance, for median is going to be m plus 1 over 2. We have already seen that. We have actually used different formulas for odd and even numbers, but you are going to see that the single formulation will be valid for any number of observations. And when you use, I'm going to show you in a minute. And when you use this logic, 25th percentile or the first quartile is going to be n plus 1 over 4. And this is going to be 3 over 4 times m plus 1. The logic, I think, is pretty much simple. So let's see how is this used. So let's say that these are our observations. So what we do here is we can directly use the formulation. For instance, Q2, which is actually the median, is going to be equal to x n plus 1 over 2. So we have 8 observations here. It is 8 plus 1 over 2. So it's going to be x 4.5. Note that 4.5 does not exist, but it lies between 4 and 5. Therefore, this is the equation that we are going to be using. And note that this is the same formulation we used for median previously. But this actually captures the whole idea very clearly. So Q1 is going to be equal to x 8 plus 1 over 4. Which is going to be equal to 2.25, I guess. Yes. So in integer values, it's going to be 2 plus 3 over 2. Well, note that there are actually different methods. When I say different methods, for instance, this 2.25 may be taken as a weighted average between those two values because 2.25 is closer to the second observation, but that much detail is not required. So Q3 is going to be equal to x 3 times 8 plus 1 over 4, and it's going to be x, let's see, I'm just going to copy here, I'm sorry, 6.25, therefore it's going to be x6 plus x7 over 2. Of course, in order to compute these values, we need to rank order these values. So it's going to be 0, 1, I'm sorry, 0, 2, and 3, and 5, and 10, and 12, and 16, and 21. And the rank ordering here, this is x1, x2, 3, 4. Well, actually, it gets boring, so I'm just going to write them in this fashion. So here, x4 and x5 is going to be 5 plus 10 over 2. You can compute the results. And this one is going to be equal to 2 plus 3 over 2. And this one, 12 plus over 2. So the result, let me write them so that it's 7.5. 2.5 and 14. So if we write them in this fashion, for instance, 2.5 and 7.5 and 14, which are equal to Q1, Q2, and Q3. This is a very nice summary of our data. So now you don't look, of course, we always need to look at the whole data points, but when somebody, instead of giving these values, when somebody tells you that these are the first 3 quartiles, you can easily imagine 50% of the data is below 7.5 and the rest is higher than 0.5. Actually, the middle 25 range resides between 2.5 and 7.5, and the other range between 50% to 75% lies between 7.5 to 40. Well, we don't know the minimum and maximum values. You can report them, of course, but it gives a very nice summary of the bulk region, I may say, of the whole data. Okay, that's all to do with the location of data. Now let's continue with measures of variability. Now, what do I mean by measure of variability? You should, let me go back to the example I talked about previously. Think about a dragon. The location of the dragon may be found by any of these methods, but none of these methods tell us about the, except maybe this one. Quartile gives an idea about the variability of the data, but the other ones, median, mode, or mean, they do not tell us anything about the spread of the dragon. Is it large or is it small? Okay, it's a single location is given, but what about the spread of the dragon or our data, or width of our data? So it says actually nothing about the variability, and you should realize, and as I said previously, variability is actually the central concept in statistics. So when we would like to measure the variability, and note that this is pretty much irrespective or independent of location, we have again different tools. Well, the first one and the associated one, another one associated with the first one, is the range. The idea is very simple. You find the maximum value, you find the minimum value, and you subtract those two. For instance, for this case, the maximum value is 21. For this example, maximum x is 21 and minimum x is 0. You can also report these values, but if you just find the range, it's going to be very much informative. Think about this information coupled with this information. The quartiles give us the location of the middle 50% between 2.5 to 14, and 21 gives us the whole range of data. So it just, you put this on the center here, the 2.5 to 14, the values. There is actually, it says that there are, of course, here 25% and here 25% other observations, but the range is not very much higher compared to these values. And interquartile range is very much associated with this calculation. It is basically Q3 minus Q1. So it's going to be equal to here, very simply, interquartile range is 14 minus 2.5. So it's whatever, 11.5. Yes. So here are two very good, nice spread measures. Interquartile range of this data is 11.5, and range of this data is 25. So you should visualize in your mind the middle 50% of the whole data covers a range of 11.5 units, whereas the whole data is more spread. Of course, it covers a range of 21 units. While there is an important distinction between range and interquartile range, note that range is a non-robust statistic. What do I mean by that? If this value were equal to 210, then the range would have turned out to be equal to 210, because the highest value would be 210, the lowest value would be 0. So the range is very sensitive to outliers. On the other hand, note that even if you change this to 210, this value would be 210. Since this is the 8th observation, and 8th observation does not contribute to Q through Q1 or Q3, any of those, these values would not have changed, and interquartile range would have remained the same. So the reason is because interquartile range gives a range of the middle portion, and the middle portion is more robust to changes in the outliers, because outliers are on the right hand side and on the left hand side. So actually, interquartile range is a robust measure, just like median is a robust measure, whereas range just like mean is a non-robust measure. Both give information. We may like our measure to be sensitive to outliers, or we may not like it to be sensitive to outliers. So usually both of these measures are reported. Okay, so just like sample mean is the most common measure of location, sample variance is the most common, and standard deviation is the most common measure of spread. And this is, I guess, you have used in this, at least in physics laboratory. And when I was a student, I should admit that I didn't understand until the statistics course what sample variance and standard deviation is. Actually, okay, you learn the calculation, but it doesn't seem to mean anything. So the idea here is the calculation, if you can read my writing here, it is simply you just take each observation, you find the sample mean value, then you do something strange. You square this one, and then you add this value, what this squared term, for all n observations, and then you divide it by n minus 1. This is what we call sample variance. Actually, standard deviation is nothing but the square root of that. Okay, that's standard deviation, maybe a very easy formulation. What does this mean? And maybe, why do I take the square root further here? Why, well, if I have sample variance, why do I need another thing, sample deviation? First of all, I try to interpret the formulation of variance. Now, formulation of variance, note that this is a measure of spread. It is the use. As you can see, it seems to be slightly complicated compared to range and interquartile range. In both of them, just the subtraction between different ranked observations, both of them. One of them, the largest, the minimum, and the other one is first and third quartile. Now, here the whole thing is a bit different. First, we find the sample mean. Sample mean is like the physics example is like center of mass. Here, let's say this is the sample mean of different observations. We have x1, x2, and x3 here. So let's say this is the sample mean. Now, what we do is, and this is a dot-dot diagram. We find the distance of the first observation to sample mean. Now, what do I mean by distance? x1 minus x bar, is it the distance? No, actually, it's not the distance yet, because distance is actually absolute value. What do I mean by that? Because since x2 is here, for instance, the distance between x2 and x, if you subtract x2 from x bar, is going to be a negative value. But distance should be positive. Why do we need something positive? Because we are interested in spread. Spread means distance from origin, either in negative or positive direction. So one could have used easily for distance, for instance, an absolute value. Now, there are reasons for why not using absolute value. Let me just mention for the time being, it's not the whole story, and it's not actually totally correct, but due to some arithmetic reasons, some algebraic reasons, since the derivative of the absolute value is difficult to handle, but as I said, that's not the whole story. Instead of the absolute value, we can use square operation. So why use square operation? When you square a value, the negative values will also turn into positive, right? So in either direction, it doesn't matter. So if the distance, if the deviation between these two values are high, then the square will be giving the square operation is going to make it even much more higher. So basically what we do is we find the squared distance of each observation from the supposedly origin, or let's say this central tendency value suggested or proposed by sample mean. Then what we do is these squared distances, we find the average of these squared distances. And what's that average? Note that these are the squared distances. So this is actually d square, call it di square, right? I take each of these terms, d1, d2, d3, and I find the average. However, in finding the average, we divide it by the number of observations. So this should have been equal to 3. Okay, but actually there is also a reason which I'm not going to talk about. Instead of and the number of observations. Here we divide it by -1. But this is very similar in concept to taking the average. As I said, the reason why we divide by, we subtract by -1 is something that I'm going to talk about later. So that's basically the average squared distance from sample mean. You can call it that way. This is what sample variance is. And okay, what about standard deviation? Well, note that the result will be squared distance. The whole thing will be average squared distance. Call it average squared distance. So the unit here will be distance squared. So it's going to be unit, whatever the unit of x, the unit is going to be squared x. So if we are talking about meters, it's going to be meter square. When you give a value, when you give a metric of meter square, and if we are used to using, let's say, meters here, then this is going to be confusing. One cannot really give a magnitude to that. For instance, if we are measuring things and these are values are 2 meter, 3 meter, 4 meter, 5 meter, let's say the variance comes out to be 15 meters square. Now you cannot, since this is not of the same unit but it's a square unit, it is difficult to visualize whether this is a large value or a small value in relation to the values that we have measured. That's why we take the square root. When you take the square root, let it be 16. So 4 meter is going to be the standard deviation. You can easily compare it with the x values that you have measured. So it's going to be easier to have an understanding of the magnitude of standard deviation. So that's why standard deviation is used by taking the square root. So an example here, this is just basically, it's going to be calculation, so I'm going to do it a little bit fast. So in order to find the standard deviation, first we find x bar is going to be 90 plus 128 plus all those 4 observations divided by 4. Just do the arithmetic. It's going to be 140.8 pounds square inch. Please realize that I also write the units. Let's say these are 4 observations, I don't know, sampled hourly in a batch reactor. Then S square is going to be equal to each observation is going to be subtracted from this sample mean, and then we square it. Basically, we find the distance square. So it's going to be 128 minus 140 minus 8 plus 2 other observations divided by 4 minus 1. Because it's averaging, but it's a kind of strange averaging later I'm going to talk about. And the result is 2,289 pounds square inch square. And here, this is what I'm trying to say. Compared to these values, and at the end, we would like to obtain an estimate or an idea about the spread of data. This is squared, so we don't like it. So S is take the square root of this 47.8 pounds square inch. So what does this mean? Read this with the sample mean. Instead of these values, somebody says that I have made different measurements of our batch reactor, pressure measurements of our batch reactor, right? And then I found, and or he or she doesn't report you these values, say there are many of these, hundreds of these there may be also. You say that just give me the numerical descriptive statistics. And he says the average value of our reactor is 141 pounds square inch. Now, does this give all information? Actually, no. Well, outliers or things like that is another story. But when you say 141, you do not know. Maybe daily to daily, one day is 1 pound square inch, the other one is 1,000. We don't know that. So he or she also reports this. 40, let's say simply to make it much more easier, 50 pounds square inch. So 140 is the location of data, and around this data, observations fall somewhat like between 50 minus 50. Note that this is not a very clear cut value. If you add this the 140 by 50 this subtracted, you are not going to find exactly boundaries to enclose this data. Still, this gives you an idea about how, where or whereabouts our data fluctuates. So it gives you an idea about the spread. If this value were equal to one, I don't know, something like this, then the spread would be very much higher. S square is the non-robust measure. And there is also an alternative formulation to compute S square, which you should be familiar. Instead of this formulation, you can also use this one. You may say, okay, this is why do we need that? Actually, later we are going to talk about expectations and things like that. So you should be familiar with this whole calculation. The idea is very simple, and it's maybe a little bit counterintuitive, because you can take xi here and take the square, then minus n bar x bar square. Actually, this seems pretty much counterintuitive to what you have learned in high school maybe. You cannot take the square of these values. Yes, for this case you can, and there's a reason for that, arithmetic reason. For those who are interested, later you may come and ask me. Anyway, so for this case, how are we going to compute? So we need two calculations here, I1 to n xi square. So this is going to be computed each term 90 square plus 128 plus square plus 1000. And the result is something like this, I guess, pound square is square. Then you obtain the second element is going to be n x bar square, which is 4 times. So you should have already calculated this value, right? And the result is 79.24 pounds square. Please note that this term cannot exceed this value. So here, this this left-hand side term on the left-hand side should be greater than this value, because s square cannot be negative. So when you subtract those two, the result is going to divide by 3, right? And minus 1 here, again do it, and you are going to obtain the same value. Okay, so the last method that I'm going to be talking about is box plot. Actually, I have taken box plot as a separate method, neither a graphical or a numerical descriptive statistics, because it's a combination of both. It's actually a graphical statistic. As you can see, we are going to draw a graph. However, we are going to be heavily using numerical statistics also. The idea is very simple. Actually, we use the first 3 quartiles, Q1, Q2, and Q3, in showing this rectangular, this box part. So actually, median of the data will be shown with this horizontal line, and the third quartile and the first quartile will be represented these lines, and we are going to draw a box here. So this is going to represent any sample that we would like to show. So this is the box part. Next comes these lines, which are called whiskers, elongated to the minimum and kind of maximum values. So actually it reads here maximum, which is maybe a little bit difficult to read. Why did I say kind of? Actually, there's a small computation here that you need to consider, and that's only the only tricky part about box plot. We are going to elongate these whiskers, not necessarily until the minimum and maximum values. There's a condition. And what's that condition? These whiskers are extended to include observations smaller than this formula. So what we do is, after we draw this rectangle, we find the interquartile range. Actually, this is our interquartile range. Then what we do is this. Starting from Q3, we multiply this interquartile range by 1.5 and add this to Q3, which is actually this formulation. So here is the idea. Observations excluding this range, so from this point to, let's say it's going to be this region. Let's say this is 1.5 interquartile range plus Q3. This value here. If there is any observation which exceeds this virtual limit, then it is going to be left as an outlier. So let's say for this case, there is one observation which exceeds this limit, hence it's not included, not going to be included in this whisker. So is the whisker going to end up here in this case? No, actually it's going to, this is a virtual limit. So we are not going to show it explicitly. We are going to end it on the next observation, and this means that the next observation is here at this point. So it means, I repeat again, there is the high, so this is x actually 1, I'm sorry, n, the largest observation, and this is xn minus 1. Xn actually is above this virtual limit, which is 1 plus 1.5 interquartile range plus Q3 value, therefore it's left outside, and the next observation xn minus 1 is below this limit, hence the whisker is ended at this point. So it's the same thing here for the minimum value. Here for this specific case, minimum values inside this limit, and what is that limit? It is actually Q1 minus 1.5 interquartile range. Therefore, if the values are within this range, right, then you end up at that value. If there were any observation here, then we would have left this, or maybe a couple of observations here as outliers, and we would have ended the whisker on the observation which is inside this limit. I don't know if that's been clear enough. I'm going to try to show it on a very simple example. Let's say that these are our batteries and these are our recharge lives. You may take this as hours. So we are going to draw a box plot. So what you do is we sort the x in increasing order first. Then what we do is we find the median, which is the second quartile, and using the formulation, since here we have actually, I think, 15 observations. Yes, so here that means n is equal to 15. So we are looking for x is equal to 8. So this is our median. And Q1, which is the first quartile, is going to be 16 over 4. I'm using the formulations I have shown previously. So it's going to be this observation. So the first quartile and the third quartile is going to be 12, which is going to be here. And actually we are halfway in drawing. This is our sample, and these are our life, cell battery life. Anyway, so here this is going to be the middle portion. The median value is 856. Please always show these values explicitly, otherwise the box plot will be meaningless. And we have 1016. And I tried to show it as much in scale as it could be, because here you should see that the upper 50 to 25% covers in a slightly wider range compared to this lower percent. So this is the interquartile range, which is the bulk portion of our data, which I call, it's the middle 50%. So let's find interquartile range. Here is going to be Q3 minus Q1, which is going to be 286. So now the question is this: are there any observation here in Xi which is greater than Q3 plus 1 minus 1.5 interquartile range? This value is Q3 interquartile range. So if you do this calculation, this is going to be equal to 1445. So are there any values which exceeds this value? Yes, we have one. Note that we could have two, that's okay. So the value that is just below this one is this one. So this is going to be the point where whisker plot ends, or whisker ends. This value here. And this one is going to be an outlier here. Again, you should show it explicitly. So the upper part of the box plot is complete. Now the lower part. This time we ask the question, are there any x value which is smaller than Q1 minus 1.5 interquartile range? This is Q1 value, and again interquartile range. And this value is going to come out to be equal to 301 if I compute correctly. So there is no values, the smallest value is 558. So there is no value here which exceeds this value. So we are going to end up the whisker plot, whisker here. So this is going to be our box plot. It simply means that the interquartile range of 50% of data is accumulated in a certain region. The lower percent, this is actually a pretty much small area, as you can see. It consists of only a cell life of about 120 hours, let's say. Then the lower percent, the lower 25%, is also covers in a small range. This is the range between 50 and 75%. Actually, this is a larger range, right? And we have one outlier here. So we can understand the distribution from this box plot, both using numerical values and graphical forms. And I think that's one of the reasons why it's almost as frequently used as histograms. And in some cases, it gives much more information. Okay, that's all we are going to talk about today.